Welcome to ES350 Lecture 8. Today we're going to look at two new topics in the design process that will move us further into the actual physical design that we are working on. We will be looking at changing our basic model into a detailed model that will give us information that will help us choose part sizes and materials and things of this sort. And then we will be looking at the fab plan and using it to lay out the list of the various parts in our design that we will be then drawing CAD drawings for, as well as laying out the fab process and setting up a bill of materials. So let's start by looking at detailed modeling. In assignment 11, we created basic models of our designs, which you should have received feedback for through my Wartburg. These basic models were based very strongly on the functional analysis that we did for our designs, and they were designed to track the inputs and the outputs and determine control variables. Common assumptions were that there were no losses and no failure. And the overall goal for this basic model was to compare the three or four different designs that we had within our group. And so the figures or the numbers that we were getting from these models were ballpark figures, not necessarily realistic, but if the same assumptions were made for all of the designs we were comparing, then they were still giving us the same trends and the same information about which one was better in different areas. So what we're going to do now is create a detailed model that has a different set of goals. We now need a model that will help us predict outcomes and analyze safety, to choose components. So do we need a shaft that is a 1/4 inch, or do we need a shaft that is a 1/2 inch? Do we need a radius of our wheel of 1/2 meter or 3/4 of a meter? These are the ultimate goal here is to finalize our design, to figure out exactly what parts we're going to need and their sizes and their materials and all of these types of things. So in order to do that, we're not going to be able to make the simplifying assumptions that we made in our basic model. This detailed model is going to help us justify the resources that we're asking for to our supervisors, and it will also show our competence as an engineer. This is where a lot of the classwork that we've taken up until this point in our curriculum will come into play as we start analyzing many of the details in our design. So on my Wartburg, there's a document called Drive Design, and this lays out some of the design considerations that go into various different types of drives. And since most of our designs in this class are based on these drives, that information will be useful. So some rules of thumb when we're dealing with gears, which many of you will be doing, is that when we're looking at losses, the rough estimate that is that each set of gears, so each pair of gears will have 85% efficiency. So if you have two pairs of gears, you're going to have 85 times 85 as its efficiency, and so your efficiency is going to drop with each set of gears that you add to your design. These losses are usually coming from mesh mismatch. So you're not going to have an exactly fitting mesh in your gears, so tooth to tooth. You may also get some losses from bearings that the gears are turning on, as well as some tooth shear stresses or tooth bending in your gears. When you're choosing gears, you need to make sure that you're not mixing pressure angles and diametral pitch. And so when you're looking at McMaster-Carr or other websites that are selling gears, make sure that your pressure angles and diameter pitch numbers are matching for your small gear and big gear in each set. This will ensure that the gears themselves will fit together. In the drive design document, there's also a list of formulas that can be used to determine the minimum pinion side given a gear size, or the largest gear that could go with a specified pinion. The pinion is just a special name given for the small gear. And so you can't have an infinite possible number of gear ratios, right? You can't have a humongous gear and a tiny little pinion. It's just not reasonable. And so these formulas give you a general rule of thumb type calculations that will tell you what the limits on that pairing will be. There's also an equation in there for a gear rack, so if you're using a linear gear type system, how those things will match together. There's equations in that document also that will allow you to examine gear tooth stress, which is important. That will allow you to examine gear tooth stress, which is important to make sure that your gear actually can withstand the forces that your design are applying to it. Especially important to give you an indication of material choice. So do you need hardened steel? Can you get away with plastic? These types of questions. Also in that document, there's equations that help you deal with sprocket chain drives, which is like what we see on our bicycles. And many of you are using those types of chain drives in your design. These are typically 90% efficient for each chain sprocket combination, and they have a moderate life and noise information, and those are requirements for some of your designs. Belt drives, on the other hand, are again 85% efficient. They typically have higher shaft loads than gears do, and so it'll be extra important to analyze the bending and deflection of shafts if you're using a belt drive. Formulas are in the document that allow you to calculate the tensions and the torque transfer requirements for using belt drives. If you're using bearings, which most of you will be to some extent anyhow, the material choice will dictate your coefficient of friction. And so you can find information about the coefficient of friction for various different materials. Even if you're just using a wood-on-wood type bearing, where you have your wooden shaft be resting on a hardwood support. That would give you, and that's not a bad bearing actually, and that will give you, you can look up a coefficient of friction for that bearing. And there's calculations provided in that document I was mentioning that allow you to figure out the power loss. So a drag torque, the torque, and times an angular velocity. And you can treat this as a statics problem to figure out the normal loads that will allow you to find the friction. Your total device efficiency, which is an important number to know for your design, is found by multiplying the efficiency of each component in your design. So as you go through all your various gears and your chain drive and all of these other things, you multiply all those together, and that'll give you your device efficiency. Some of you might be looking at using flywheels, which will allow you to convert a periodic input into a constant input. Not necessarily useful for a bicycle input, because you don't really have a periodic input with a bicycle. You have a constant or a continuous input from the 2 feet that offset each other. But at least one of you is maybe doing a pull drive type setup, which would benefit from a flywheel. Formulas are provided in that document. The other thing that's really important to analyze is the bending of some of the key components in your design. And so you think back to your equations from ES350. Let me know if you need to borrow a textbook. and take a look at the bending and the deflection. Because the importance here is if the shaft bends, even if it doesn't fail, if it deflects enough, your teeth will no longer mesh in a gear, or your chain won't have the tension it needs to stay on the sprocket. And so even just bending in a shaft is going to be important. So look at, not in everything, but look at the key components where you're worried, especially if you've got a cantilever support, for example, or if you've got a highly loaded shaft. Take a look at the bending in some of those components. The goal here is, when you're picking numbers, is probably to use commonly available parts. So if you take a look at McMaster Car, this is, so at McMaster.com, this is an online store that sells a lot of components of various different types. And so it'll give you an idea of what standard sizes are, both in the metric system and in the US standard system. And so picking a shaft that's a quarter instead of 0.253, for example, will allow you to buy your shafts more easily and therefore more cheaply, if you can get away with a quarter. If not, you might want to size it up to the next standard size instead of picking this strange size, even though that might be the optimal one that your model is telling you. So your assignment is outlined on the assignment document, but in summary, you're going to start with your basic model, and then you're going to include losses for each of your components, calculate your gear efficiencies if you're using gears, figure out your bearing friction for your bearing supports of your shafts. If you've got generators or pumps in your model, figure out their efficiencies, which will come from a website selling them. Improve your basic model by including all of these various losses. Calculate your overall design efficiency by multiplying the efficiencies of each of your components, and test for failure by looking at bending, alignment, and things of that sort, stress and bending calculations for your gear teeth, for your shafts, for various other key components. And make sure you're including a factor of safety in these calculations. The other tool that I wanted to talk to you about today is the fab plan, and getting started on this fab plan. And there's three major components to the fab plan. One is the fab plan itself, where you actually lay out the list of all the components in your design and whether or not you're going to buy them and what tools are going to be necessary to build them or to assemble them, and how much time that's going to take, and this type of thing. So that's the fab plan itself. The fab plan will also include the CAD drawings for all of your parts, whether they're bought parts or parts that are going to actually be made, machined by you or by the entrepreneur in your third world country. And so those are all of the various drawings. And then you've got your bill of materials, which is actually the things that you're going to buy, whether it's raw materials or actual parts, gears that you're going to buy, or a chain that you're going to buy, or something of this sort. So let's talk a little bit about engineering drawings first of all. This is a form of communication. And so when we talk about technical communication in engineering, engineering drawings, CAD drawings, are actually included in that technical communication abilities, right? So technical communication isn't just writing reports or memos, making presentations. Drawing these and making these engineering drawings is a form of technical communication that's very important in engineering. It's a formal and precise way of communicating this information. And the key information coming through the drawings is the shape, the size, the features, and precision of the item that we're creating. There are standards in industry, and depending on the company that you're working for, you may have different standards. So pay attention to training and instructions given. And many of the CAD software packages have these standards built in, so you just have to specify them. And the information that a drawing gives usually includes some sort of 3D view, so you have a picture of a 3D object on your drawing. Then you have projected views, so top, front, side, those types of things. And you're going to include as many as you need in order to indicate all of the various dimensions that you need to specify. So sometimes you can get away with a single projected view, and sometimes you need 3, 4, 5 of them. You can also have cross sections, right? So this is where you're zooming, you're cutting something in such a way to show internal features. In the table part of your diagram, your drawing, you're going to give the part name, material info, what material it's made out of, who designed it, so your name and the date, and whether or not it has been modified, that type of information, and what a standard tolerance would be for this part. And then you're going to specify all of the various dimensions so that somebody could take your drawing, go into a machine shop, and actually build your part. So here's a sample drawing. Right, so we have the 3D part in the upper left-hand corner, and then we have a series of projected views. So we have a side view, and then we have the front view and the back view, the top view and the bottom view, and all of them show the various dimensions of various holes, where they're at, all of these types of things. And there's a method that is used that dictates how those dimensions are put on your drawing. CAD software has these conventions built in, so oftentimes they will give you those. Sometimes it comes from how you created the drawing. And oftentimes, if you're doing a lot of CAD work for the company that you're working for, you will go through various trainings on how to create tolerances, how to dimension specifically for manufacturability, things of this sort. The table I was talking about is this information down at the bottom, where you're making notes for the person who's manufacturing it, but also indicating who you are, when it was modified, when it was first drawn, what the tolerances are, what it's made out of, this type of thing. We also have a type of drawing that's called an assembly drawing, and this is how all the various components actually fit together. So component A gets connected to component B, which gets connected to component C, this type of thing. So you're going to take all of your various components and put them together into an assembly drawing. And once again, the CAD software can do this for you. This is also shows you what the final product's going to look like assembled, but also shows you an exploded view that shows how they actually, the order in which they get put together. It'll give you a list of the various components in your part, the number of repeats. So if you have 4 chains, for example, that you're going to use, you'll have that indicated on this diagram. And once again, information about what this is, who drew it, this type of thing. So the fab plan is a tab in your DMADVER document. And this is the idea behind the fab plan is we're going to look at our entire design, and we're going to break that up into assemblies and sub-assemblies and then into components. So the goal is to have a list of every single component that is in our design. So everything from the shafts to the screws that are holding it together, to the boxes, to the pieces of the 4 pieces of wood that we're making our box out of, everything. So we're going to get a list of all of these components and also the sub-assemblies and assemblies that they're in. Then within each of those, for each of the components, we're going to identify it somehow in a code that links that component to the drawing that we're going to make in CAD. right? So this is our formal list, and it's going to be linked somehow to the drawing number. So I would recommend, if you have several sub-assemblies, set up some sort of code system. So subassembly 1 part 1, subassembly 1 part 2, this type of thing, that gives you an organization system for your components. We need drawings for every single one of these components unless it's a fastener. So if you're talking about screws, screws should still be listed as components, and you're going to size them and figure out how big they need to be and how long they need to be and things like this. They're going to be on your bill of materials, but you don't have to actually draw those. Everything else, whether you're buying it or making it, needs to be drawn so that we can actually have a good looking assembly at the end. So then in your fab plan, once you've got your components all listed, your assemblies, sub-assemblies, and components all listed out, each of the components gets a drawing number, and then indicate who's going to be drawing it. Everybody on your team has to draw at least 2 parts. So talk about things with your team. And if you've got a CAD expert on your team who knows CAD really well, maybe they're going to do the more complicated parts. And the people who don't know CAD very well are going to test their CAD skills on some of the more simple parts. So split them up based on your CAD experience, but indicate in the column who's going to be drawing them. That is the point that I want you to get to today in the fab plan, right? So listed out assemblies and sub-assemblies and all your components. Create some form of code to organize those components by drawing number that you're going to use on your drawings, and figure out who's going to draw each component. Then after that's complete, we're going to look at other parts of the fab plan, which you can start today, but I'm not necessarily expecting you to have these done. But what we're going to look at for each of the components, we're going to look at the processes needed to manufacture it. If we're actually just purchasing it, just indicate that it's purchased. But if we're building it in any way, are we going to be drilling it? Are we going to be turning it? Are we cutting it, sanding it, welding it? This type of thing. For the sub-assemblies and the assemblies, you're going to be talking about similar things for assembly, right? So if we're taking 4 pieces of wood and we're gluing them together, then our process would be gluing, and that's going to show up under the box for the sub-assembly, right? Whereas to make the pieces of wood, we might have been cutting and sanding, right? So then, for each of those, looking at those processes, we're going to talk about the types of tools that we're going to need in order to do those processes. So when we're sanding something, are we sanding it with a belt sander? Are we sanding it with a circular sander? Are we sanding it by hand with sandpaper, right? Those are different things. So talk about the actual tools. Do we need a lathe? Do we need a milling machine, a drill press, a screwdriver? Are we using a hand tool, or are we using an electric screwdriver? Is it a bandsaw or a table saw? Is it a little hand saw? These are the types of things we're doing. Now the reason we're listing this is going to dictate who and where these parts can be made, right? So if we need a metal lathe, then we need to find a machine shop that has a metal lathe. Those might be in the US, or there may be a specialized machine shop in our developing country that has that lathe, but that's going to dictate where we're going to have to manufacture this. Then estimate the time needed for each of your parts to be made. Now these are going to be guesses at this point. Unless you have a lot of experience with fabrication, it's going to be very difficult to do this, but come to a consensus as a team as to how long each part might take to be made and each sub-assembly to be assembled, etc. And then finally indicate which of these are critical, right? So if it's critical for this gear to mesh with this gear, or this shaft hole to be very much aligned, or the whole thing is going to fail because the gears aren't going to mesh and the things won't turn, then indicate that, because that's going to be where you're going to watch the primary tolerances. And then the final part of the fab plan is your bill of materials. And this is going to help us determine the supplies that we need to manufacture, as well as the cost of our total device. So we're also going to be looking at where these parts are going to be purchased. So McMaster Car, the website I mentioned earlier, is a great value. Looking at local Lowe's or Home Depot, but also remembering that we aren't going to necessarily be buying them in the U.S. If we're looking for lumber, for example, and we're looking at lumber in the developing world, it's going to be costed differently. So see if we can find some estimates for that. For parts that we're buying in the U.S., indicate with a supplier, McMaster Car or whatever other website. Talk about and actually find it on the website, give us a reference to it, indicate the cost per part, and give us a link as if we were going to go and buy this thing. For parts that you're making, you're going to have to buy the raw material, right? So if you're cutting something out of steel, you're going to have to buy that steel. What shape are you going to buy that steel in? Is it going to be bar stock? Is it going to be a cylindrical stock? These types of questions. Where are you buying it from? What's the supplier? Give me a reference number or something that I can find it at that supplier. What's the cost and what's the link to it, right? And then indicate which parts are going to be using it. So if you might buy a 2x4 that's going to allow you to make 2 or 3 different parts, right? So just indicate, use your drawing number, right, that links to the component. Indicate what components are going to be made out of this raw material. Right now, leave the conversion to bulk alone, and I'll be looking up some numbers that will help us convert to bulk. So the idea, if we were only to make a prototype, it's going to be more expensive than if we're going to make several thousand of these or several million of these. So depending on what your plan is, how many you're going to be making, we may be able to reduce our costs by buying our material in bulk. So as a review, what you're going to look at doing today is work on your detailed model. Start from your basic model and then start adding in losses, adding in strength and materials type analysis, that type of thing. Work on creating your list of assemblies, sub-assemblies, and components in your fab plan, and I would recommend each of those. Assembly gets its own line, then under that you've got your list of sub-assemblies, and under the sub-assemblies you've got a list of all your components, so that you have space in your fab plan then to indicate what processes are necessary for each of those. And then start working on your list of the parts that you're going to purchase, the bill of materials. Start looking at websites, start seeing where you might order things, what things are you going to actually have to build versus buy, because as you need to figure those out so that when you draw the CAD drawings, you're actually drawing the part that's really going to go into your thing. Next week, we're going to finalize your detailed model, get your questions answered, work with me on that. We're going to work on the CAD drawings, so you can start this week if you want to, but we're going to continue working on those in class when I'm around to try to answer CAD questions if you're not experts at CAD. And and so that's what our next week is going to look like.